Hello, this is Dr. Strickland. In this video, we will finish our investigation of E2 reactions and talk about E1 reactions as well. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. All right, so just need to finish up just a little bit with E2s. And remember that with E2 reactions, just like with substitution reactions, these letters and numbers in the symbol mean something. The E stands for elimination. And the 2 stands for bimolecular transition state in the rate limiting step. And remember that in an E2 reaction, like with an SN2, there is only one step. So if there's only one step, it has to be the rate limiting step. And both the alkyl halide and the base are both involved in that transition state. So the rate for an E2 reaction, just while we're here, will involve both the concentration of the alkyl halide and the concentration of whatever it is that's functioning as the base. Okay. All right. So the last thing that we need to talk about, with the exceptions to Zaitsev's rule, has to do with the leaving groups. If you have a good leaving group, then Zaitsev's rule is followed. But if you have a poor leaving group, like a fluoride ion, then the less hindered alkene is preferentially formed. And the reason is because fluoride is the strongest base of all of the halides. And because of that, it leaves slowly. And as it leaves slowly, you get a development of negative charge right here on that carbon. So that means you have a carbanion intermediate rather than a carbocation. And carbanion stability is the opposite of carbocation stability, because you don't want hyperconjugation pushing little bits of electron density into a carbon with a negative charge, because that makes it less stable, not more stable. And so for that reason, if you have a poor leaving group, you're going to form the less hindered alkene because of this difference in stability for the intermediate. So here's our alpha carbon. Here are our beta carbons. The two possible products are these two, and like this and this. This one would have E and Z isomers. Now, Zaitsev's rule would say this would be the major product, but because we've got a poor leaving group, that means that this guy is going to be the major product. All right, so one last thing, when you look at the relative reactivities of alkyl halides in E2 reactions, for one thing, methyl halides can't take part in elimination reactions at all, because you have to have at least 2 carbons. You have to have both an alpha and a beta carbon to make that go. But what we find is that within these 3, this one is the slowest, and this one is the fastest. Now, this is an E2 reaction, but the reason that you get a faster E2 reaction going this way is because you form, in general, a more stable alkene. That is a more substituted. All right. So when Zaitsev's rule is followed, under normal circumstances, that's what you would see. All right, so let's see how E1 is different. So E2 goes with SN2, and E1 goes with SN1, and that means that an E1 reaction involves a carbocation intermediate. So we've got our alpha carbon And we've got, in this case, because this is a tertiary alkyl halide, 3 beta carbons. And if you mix it up with some water, what you get is this. This alkene right here, which would be 2-methylpropene. And then the conjugate acid of your base and your leaving group. And we'll just do that. Okay, so this is E1. Analogous to E2. Elimination. Unimolecular transition state in the rate limiting step. And like with an SN1, this is the formation of the carbocation intermediate. Okay, so let's see what that looks like. So we've got our alkyl halide here, and the first thing it's going to do is form its carbocation. All right, so there are the carbons of the structure, and we lost our bromide right here. All right, so this is our alpha carbon. These are the 2 beta carbons that I'm not going to do anything with. And I'm going to draw out the hydrogens on this beta carbon because that's where we're going to lose one. So let's do this just to remind ourselves of why we did it that way. Okay, so now we've got our water, which is going to function here as the base. And what's it going to do? Well, it's going to remove one of these guys. And you're going to hold that down. And so instead of having, both the bond break and the bond form in the same step, they happen in different steps. All right, and so I'm going to show you a different way to do this. All right, if you want, you can, instead of writing CH2 like this, you can turn it around like this so you can show the bond directly between those carbons. This is a condensed structural formula thing, and it's fine to write it either way, whichever way you would like to do. All right, and these are our other products here. The hydronium ion, which has too many electrons up there. Okay. And my bromide. All right, as far as relative reactivities go, it turns out, well, first of all, we have to take this one out because it doesn't have enough carbons to do an elimination. Turns out that in terms of faster and slower, this one is still the slowest. And this one is still the fastest. But the reason is different. So we still have a faster elimination reaction, in this case an E1 reaction. But it's not because we're forming a more substituted alkene, it's because we're involving a more stable carbocation intermediate. All right, so a more stable carbocation intermediate is involved. Okay, all right. A couple more things. First of all, we can come down here before we talk about this. If you have a carbocation intermediate in anything, remember that you have to check it for carbocation rearrangements. Okay, always, no matter what reaction we're talking about. If there's a carbocation, check it for 1,2 hydride shifts and 1,2 alkyl shifts. Now, E1s do follow Zaitsev's rule. And so we are going to form the more substituted alkene when we can. So we've got these two are methyl groups, and this is a methylene. So if we remove it from the methylene, first of all, it would look like this. We remove it from one of these methyl groups, and I'm going to remove it from this one. It would look like that. And count my carbons, make sure I've got everything. 1, 2, 3, 4. 1, 2, 3, 4. Good. Okay. So this is a di-substituted alkene. This is a tri-substituted. So the tri-substituted alkene is the one that you will form as the major product. No E's or Z's stereoisomers with either one. This one because there are two hydrogens attached to that vinylic carbon, and this one because there are two methyl groups attached to this vinylic carbon. All right, so that is the story on E1 reactions. If you have any questions, please send them to me.